Okay, so looking at population mean. Okay, so we're looking at population mean here, and we want to apply the same idea of a confidence interval. Okay, so again, I suppose I'm conscious that we're not necessarily watching these in order or relating them back to each other. So a confidence interval again is a range within which we think the true value will lie. Okay, we are looking or need to know how to construct confidence intervals for population mean and population proportion. Okay, we're looking here at population mean. What we want is we want to be a certain confidence. Okay, we want to be 95% confident that the actual value for the population mean, which is represented by mu, falls within this range that we've constructed. Okay, generally that is constructed based off our sample, okay, and the sample mean that we found, and the error, okay, the margin of error. So we say basically that I take samples, okay, and I find all these sample values and these sample means. And we are basically saying, yeah, okay, I got a sample mean, but these sample means could be wrong. Okay, this sample mean could be far off from the actual value here. So I need to account for some potential error. So what we look at is we look at the standard error. Okay, we look at kind of for this distribution, how wrong do these sample means tend to be? Okay, on average, like what's the average wrongness, if you like? Okay, to put it better or more kind of accurate, we're basically looking at on average how far are these sample means from the true population mean. Okay, and if you're kind of following the words I'm using, I'm really referring here nearly to standard deviation. Okay, I'm basically saying in terms of standard deviations, because remember that's how that was defined, it's kind of the average distance from the mean. I'm saying here how far are these sample means from the actual mean. And when we remember that these sample means form their own distribution, I'm basically looking for the standard deviation of that distribution. Okay, and that standard error was denoted by sigma x bar. Okay, and we met that. I suppose I would have introduced that a little bit in the previous video and kind of looked at how that relates here. We're using that central limit theorem. Okay, by using that we can be kind of confident that sigma x bar can be used here. And it basically is a measure of how far from the average value we can kind of expect these sample means to be. Okay, what's the kind of standard deviation here on the whole? And then to convert that from just a standard error to a margin of error is where we include the 1.96. Okay, and again, I looked at this a little bit and it might be worth going back to just to have a quick kind of look at the population proportion video because I maybe introduced that a little bit there. But the general idea is if I could create a normal distribution here and use the values of plus 1.96 and minus 1.96, then I am including 95% of information between those two values there. So basically the probability that Z is between minus 1.96 and plus 1.96 actually works out at 95%. Okay, why that's useful for us is it means we can be quite confident, because 95% is quite confident. I can be quite confident that my value, my true value of my parameter lies within this range. Okay, what's important here is you need to make sure that you are including the 1.96. Okay, because we are basically saying we need to be kind of within that 95% confidence range. Okay, so for the margin of error, I'm including that 1.96 to account for that 95% confidence as well. Okay, my sigma over root n is my standard error. So we said that's kind of the standard deviations from the mean there within those sampling distributions there. And then the 1.96 kind of being included within that is me maybe accounting for how many standard deviations I'm willing to be away basically from the mean, which is only 1.96. Okay, so looking at constructing that into a confidence interval, then basically we will be adding and subtracting that error to my sample mean. Okay, and that's going to lead me then to my confidence interval. So we look at an example and we'll get into a question then on that. The lifespans of a particular brand of light bulb are normally distributed with an unknown mean and a standard deviation of 100 hours. So that's sigma. A random sample of 25, that's n, has an average lifespan of 1,200. That's X bar, sample mean. Construct a 95% confidence interval. So let's look at that. My 95% confidence interval is X bar plus the error and X bar minus the error. Okay, so there's an actual distance here across the interval of 2 errors. So one error taking me from here to here, and another error taking me to the far side. So a distance of 2 errors, but I'm adding and subtracting at either side. Because this is population proportion, or because this is population mean, excuse me, that I'm calculating here, I need to make sure that I use the formula for population mean, which uses the standard error, sigma x bar here. Sigma x bar, again, given in your formula and table spec for you. So filling in what we can here, 1,200 plus 100 over root 25. And again, I'll forget my 1.96 as well. And you can see what I mean. Very easy to forget here, but very, very important. So let's fill in all of these values here then. .96 times 100 over root 25. So 1239.2. And again, we'll subtract that also to get 1160.8. So we're basically saying that we can be 95% confident that the mean lifespan of these light bulbs is within 1160.8 hours and 1239.2 hours. Okay, still fairly accurate there. Okay, if we consider the sample of 1200, we're allowing ourselves in or around 40 either side there, which seems quite reasonable really for a margin of error there, given that the lifespan's quite large and our sample is actually quite small relatively. We're only looking at 25 light bulbs. So as we've kind of said, or as we maybe should kind of imagine here, looking at the standard error, as n increases, the standard error decreases. So if I want to be more accurate or more sure or have less error, I need to have bigger samples. Okay, you're kind of looking at that nearly like a limit there. Okay, as the limit as n goes bigger, and the limit obviously as n goes bigger, then would be no error at all. Okay, and that obviously would be then taking n as large as possible, which of course then is just the population. So it all kind of lines up to what we would imagine here. So we'll look at one more example here. I'm going to focus on the A part of this example. The B part's kind of about constructing confidence intervals at different levels, which isn't necessarily relevant to what we're looking at here. So the IQs of 400 randomly selected students showed a mean of 107. The standard deviation is known to be 15. Calculate a 95% confidence interval. So let's fill out what we know. N is 400. The mean X bar is 107. The standard deviation, if the population is 15, so that's sigma, we're constructing a 95% confidence interval for the population mean. So that's X bar minus 1.96 sigma over root n, and X bar plus 1.96 sigma over root n. So 107 plus 1.96, 15 over root 400, and 107 minus 1.96, 15 over root 400. So let's fill all of this in now. So that's 108.47, and subtracting it gives me 105.53. So I'm basically saying again, 95% confident that the IQs for randomly selected students would fall between 105.53 and 108.47 here. Okay, looking at this question, okay, I'm conscious there's no real reference here to the original distribution being normal. However, the sample size is over 30, so I'm content, following my central limit theorem, to take that as being normally distributed. Okay, I suppose what we would have looked at as well with normal distribution is that IQs do tend to be normally distributed, so in this case the parent distribution is probably normally distributed also. So we're kind of covered on both counts there. But basically, looking at all of these questions here, in terms of our confidence interval for population mean, following the same idea that we've already identified when I looked at it for population proportion, and really we could have tied the two together probably, but that idea that we put our parameter in the middle and we look at the sample parameter either side, adding and subtracting the error to that sample parameter, allowing ourselves that kind of range either side of the sample parameter, and then saying that the true value would lie within that range somewhere. Okay, and making sure that we don't forget our 1.96 in this case to allow for that 95% confidence. Okay, kind of allowing ourselves to be kind of within that 95% range.